All right, so now we're going to take a look at some basic bonding concepts. Earlier, we looked at ionic bonding, and we saw that ionic bonding involved the transfer of electrons from metals to nonmetals. And the reason for that was so that those species were able to become more stable. So metals become more stable by losing electrons. They adopt positive charges as a result. Nonmetals can gain those electrons to become negatively charged anions, and they become more stable as a result. Now, there's a third way by which our atoms can become more stable, and that's by sharing electrons. And the underlying principle behind, again, all of these, whether something is able to lose or gain or share electrons, is stability. And the elements on the periodic table that are the most stable in terms of their electrons are the noble gases in group H. And they typically are going to have 8 electrons in a valence shell, which is where the term octet rule comes from. Right? So octet rule, yes, it's a rule, but there are exceptions. We'll write that right away. There are exceptions to the octet rule, which is why instead of saying the octet, we usually say the elements want to lose, gain, or share electrons to achieve the electron configuration of the nearest noble gas. Now, as a very simple example, we have fluorine. We have fluorine atom on the left side, and the fluorine atom on the right. We have a Lewis-dot structure. Lewis-dot symbol for fluorine with 7 valence electrons. Another fluorine with 7 valence electrons, and these can actually help each other out by, instead of transferring, losing, or gaining electrons, they can actually share a pair of electrons between them. So this shared pair of electrons here is what the covalent bond is. This is different than the ionic bond where electrons were transferred and we had charges. Here we don't have charges, we have the sharing of electrons. So we can think of each of these electrons that are being shared as belonging to both of the fluorine. So sharing, we would normally, these two belong to both of these fluorines. Other thing to keep in mind as we go through this section is, again, we're going to focus only on the valence electrons. The core electrons, the inner electrons, they don't really contribute to bonding or chemical reactions. It's the valence electrons that are the most important. So when we write our Lewis-dot structure, for example, like a combination of two Fs, as you can imagine, if I combine two Fs together, I get S2, the fluorine molecule. It's an element still because it's made up of two of the same types of atoms, but now it's a molecule. We have two things combined together. So when we share that pair of electrons between the fluorines, we represent that shared pair of electrons with a line, specifically a single line. And that represents a single covalent bond. And that means, when you see that single line, is that two electrons are shared. What also left over on the outside to make sure that the fluorines are happy, that they're stable, is you have these pairs of electrons that are not involved in bonding. So, for example, this fluorine has 3 of these, 3 pairs of electrons. So this is called a lone pair of electrons, or sometimes called a non-bonding pair. Or non-bonding pair. They're not involved in bonding, in other words. So if I look at the fluorine on the left and I highlight the electrons that belong to it, say 3, I have these 8, right? That are in yellow. The 3 lone pairs and the 2 shared pairs of electrons. The fluorine on the right also has 3 lone pairs, so that's 6 plus also sharing those. So both of these are happy. In other words, they're more stable, connecting to each other via a single bond rather than being by themselves. So what we just drew is an example of a Lewis structure, and we've been using Lewis symbols before for the elements. Now we're putting these together in what are known as Lewis structures for our molecules. And as we saw previously, we have a shared pair of electrons that would be represented by in most cases it's a dash or a single line as a pair of dots. And then our lone pairs are also filled with pairs of dots in the outside. So in the case of water physics, we'll go through how we draw the Lewis structures for molecules. Water actually is going to look like this. So I have an O in the middle, and I have two hydrogens on either side connected via these single bonds. Two of these single bonds. And on the oxygen, I still have two lone pairs. Okay, so if you think of my oxygen now, it has two, 4, and then it's got 6 and 8, so we're happy. The hydrogen is a very special atom in that it doesn't need an octet, it only needs 2 electrons to be happy. And each of these hydrogens first have to here. For that hydrogen, and then there's 2. So in addition um, to elements forming single bonds, we also have the possibility of forming different types of covalent bonds. So for instance, if I have instead of having fluorines, let's say I had something like an oxygen. In here, oxygen, as we know, is in group 6. So it's got 1, 2, 3, 4, 6 valence electrons. It wants to have 8 to be happy. It needs 2 more. I have another oxygen over here. It also has 6. 1, 2, 3, 4, 5, 6. So it also needs 2. Guess what they can do to each other? They can share one pair of electrons, and they can share a second pair of electrons. So now this oxygen on the left side has 2, 4, 5, 6 now, 7, 8. And the one on the right has 2, 4, 5, 6, 7, 8. They're both happy. They're satisfied that rule. When we draw the Lewis structure, with this combination, we end up with both. You have 2 lone pairs left on the oxygen on the left, another O on the right with 2 lone pairs, and then connecting both oxygens, we have 2 pairs of electrons. So we have one pair of electrons, a single line, a second pair of electrons, second. So this then, when you see these 2 lines, instead of a single line being a single bond, we call 3 lines a double bond. So a double bond, 2 lines, and in a double bond, guess how many electrons are shared? 4 electrons shared in double. Right, so we have single bonds, the single lines, double bond, which are double lines, and we can probably get there in the building. If I have a nitrogen, which is in group 5, so it's got 1, 2, 3, 4, 5. There was if I have another nitrogen on the other side, it also has 5. 1, 2, 4, 5. They want to have 8 to be happy. They can share one pair of electrons. They can share another pair of electrons, and they can share a third pair of electrons. So the nitrogen on the left side has 2, 4, 6, 8 electrons. The nitrogen on the right has 2, 4, 6, 8. Right. So we're treating the shared electrons as belonging to both of the ends. So both nitrogens have their octet. So we can simplify this diagram and have a nitrogen on the left side with a lone pair left over, nitrogen on the right with a lone pair, and now these are connected via 3 pairs of electrons. That is called triple bond. And in the triple bond, we have 3 lines, each line representing 2 electrons. That would be 6 electrons. So you're going to see several examples of single bonds, double bond, triple bond, the combinations of these. And the underlying principle is having that octet to make the electrons, to make the atoms. Okay, so when we talk about Lewis structures, again, we're going to see a variety of ways to represent the structures. When you see these lines, okay, a single lines, 2 electrons, And the more lines you see, right, the more electrons are represented. The lines represent shared electrons, bonding electrons. The dots on the outside, those are non-bonding electrons, also known as lone pairs.